everyone, welcome back to our discussion on infinite series. So in today's video, we will discuss about the limits of a sequence. So to start, let me first discuss the objective of this lesson. So at the end of this discussion, you should be able to determine whether a sequence converge or diverge. And the primary focus of this lesson concerns sequences whose terms approach limiting values. So such sequences are said to converge, like for instance, if you're given a sequence of the form 1 over 2 to the n power, wherein if n is 1, we get the first term of the sequence, which is 1 over 2 to the 1 or 1/2. If n is 2, then you will get the second term, which is 1 over 2 squared or 1/4. And then for the third term, when n is 3, you get 1 over 2 cubed or 1 over 8, and so on and so forth. So these are called the terms of the sequence. But if you can observe, as the value of n increases or approaches infinity, the terms of the sequence converge to 0 as indicated in the following definition. So let me define the limit of a sequence using this definition. So let L be a real number. So the limit of a sequence denoted by a sub n is L, written as limits of a sub n as n approaches infinity is equal to L if for each epsilon greater than 0, there exists m greater than 0, such that the absolute value of a sub n minus L is less than epsilon, or the distance between a sub n and L is less than epsilon whenever n is greater than m. If the limit L of a sequence exists, then we can say that the sequence converges to L. But if the limit of a sequence does not exist, then the sequence diverges. Okay, so graphically, this definition says that eventually for n is greater than m, so this is to the right of this value m, and epsilon is greater than 0, meaning positive, the terms of a sequence that converge to L will lie within this band between these two lines, L plus epsilon and y equals L minus epsilon. So if a sequence agrees with the function f at every positive integer, and if the function f of x approaches a limit L as x approaches positive infinity, then the sequence must converge to the same limit L. Okay, so we can now define this using this theorem. So let L be a real number and let f be a function of real variable, such that the limits of the function f of x is L as x approaches infinity. And if a sub n is a sequence that the function f of n is equal to a sub n for every positive integer n, then the limits of a sub n is L as n approaches positive infinity. Okay, so as an example, suppose we are asked to find the limit of the sequence whose n term is given by a sub n equals 1 plus 1 over n quantity raised to the n power. So to define the function, we replace all the n variable by x to get 1 plus 1 over x quantity raised to x. And if you can recall in Calculus 2, under the topics indeterminate form, when you evaluate the limits of 1 plus 1 over x quantity raised to the x power as x approaches infinity, the limits of this function is indeterminate. This is infinity raised to infinity. But by taking if you let this assure y, tapos you take the natural log of both sides, and then you apply the properties of logarithmic function, and eventually you evaluate the limits of the function 1 plus 1 over x, the limits of the function will eventually give us this value e. Okay, so after evaluating the limits of this function, we will now apply theorem 9.1 from the previous slide, and we can therefore conclude that the limits of this sequence whose n term is given by a sub n as n approaches infinity is also the same as the limits of 1 plus 1 over n quantity raised to n as n approaches infinity is equal to e, because from this discussion, the limits of this function is e, so therefore the limits of a sub n is also equal to e. Okay, so there are two types of sequences. The first type are those sequences with limits or with limiting values, and the second type are those sequences without limiting values. So what we have learned in the previous slides are sequences with limiting values. But how about those sequences without limiting values? So there are two different ways in which a sequence can fail to have a limit. So one way is that the terms of the sequence increase without bound or decrease, the second type, or decrease without bound. So these cases are written symbolically as shown below. So for the terms, for the sequences whose terms increase without bound, symbolically you can write this as limits of a sub n as n approaches infinity is equal to infinity. And for sequences whose terms decrease without bound, we can write this in this notation as limits of a sub n is negative infinity as n approaches infinity. Okay, so let us now discuss the properties of limits of sequences. So suppose you're given two limits of a sub n as n approaches infinity is L, and the second one is limits of b sub n as n approaches infinity is equal to k. So the first property is called the scalar multiple property, wherein when you take the limits of the product of the scalar c and the n term of the sequence a sub n as n approaches infinity, the limits is c times L, where c is any real number. Actually, you can distribute the limit sign to each of this factor for the constant and for the n term of the sequence, which is a sub n. So you can write this as limits of c as n approaches infinity times the limits of a sub n as n approaches infinity. But since we know that the limits of the constant is always a constant, and the limits of a sub n is given in this theorem, that the limits of a sub n is L. So because the limits of c is c and the limits of a sub n is L, so the limits of the product is equal to CL. Okay, next, the next property is called the sum or difference. So in this property, we take the limits of the sum or difference of the n term of two sequences, a sub n and b sub n, as n approaches infinity. So again, we can distribute the limit symbol to each of this term, or to each of the n term of the sequence. So you get limits of a sub n as n approaches infinity, plus or minus the limits of b sub n as n approaches infinity. But from the given, again, the limits of a sub n as n approaches infinity is L. So we get this, plus or minus the limits of b sub n as n approaches infinity, which is given in this theorem, that this is equal to k. So therefore, the limits of the sum or difference of a sub n b sub n as n approaches infinity is equal to L plus or minus k. Okay, the next property is called the product property, wherein if you take the limits of the product of a sub n b sub n as n approaches infinity, you can write this as limits of a sub n as n approaches infinity times the limits of b sub n as n approaches infinity. But we know that the limits of a sub n as n approaches infinity is L, and the limits of b sub n as n approaches infinity is equal to k. So therefore, the limits of the product a sub n b sub n as n approaches infinity is equal to Lk. Okay, the last property is called the quotient property, wherein when you take the limits of the quotient of the n term a sub n and of the first sequence over the n term of the second sequence, denoted by b sub n as n approaches infinity, this is equal to L over k. Again, we can distribute the limit sign to the numerator and denominator to get limits of a sub n as n approaches infinity all over the limits of b sub n as n approaches infinity. But again, from the given, the limits of a sub n is L, and the limits of b sub n as n approaches infinity is equal to k. So therefore, the limits of the quotient a sub n over b sub n as n approaches infinity is equal to L over k, provided that b sub n is not equal to 0 and k is not equal to 0. So in summary, the limits of a sequence a sub n is said to be L as n approaches positive infinity if for every epsilon greater than 0, there exists m greater than 0, such that the absolute value of a sub n minus L, or the distance between a sub n and L, is less than epsilon whenever n is greater than m. If the limit L of a sequence exists, then we can say that the sequence converges to this value L. But if the limit of a sequence does not exist, then the sequence diverges. Also, by definition, if f is a function of a real variable such that the limits of f of x is L as x approaches positive infinity, and if the sequence a sub n such that f of n equals a sub n for every positive integer n, then the limits of a sub n is L as n approaches positive infinity.